everyone. Today we'll be talking about, as you see on the slide already, about the locks, and this talk will be in two parts. It will be a little bit theoretical at the beginning, but then we will go to the practical part. Unfortunately, it will be not so interesting maybe as previous talks from the terms of practicality, and also I'm not as great as my speaker that shared the same surname, so it will be not that not a lot of jokes will be here, unfortunately. So I will set up my time, stopwatch to check whether to stop, because my talk ranges from 25 minutes to 1 hour. So we will see how lucky I will be right now. Okay, so this is the joint work with my PhD student and other students, and also my colleagues from Nizhny Novgorod, from Anton Malakhov and Andrei Churbanov. Taras will deliver the similar talk concurrently or parallelly in St. Petersburg. So we kind of use multiprocessoring already. So let's skip this, I already presented. So what my talk will be about, it will be split into two parts. The first is a theoretical, where I will remind you what mutex is and how it is usually implemented in the wild in the term from concurrency. Then I will briefly talk about lightweight threads or coroutines, as you know, briefly, because mostly I guess already worked with coroutines a lot. And after, I will go on how you have to adapt the mutexes for coroutines if you want to call from them, and show you some experiments on the results. Let me start. So we will start from mutex. Mutex, as you know, it's mutual exclusion. I will be telling mostly locks. Mutual exclusion is mostly just to make an exclusion for the threads. So only one thread comes to the critical section, or somebody wants to update something. You take a lock, go there, and go outside. This is mutex. Locks are a little bit more complicated, but in this talk we will be talking about this basic mutex or lock understanding, because there are read-write locks and many others. So we have only two operations. We have a simple operation lock, and we have a simple operation unlock. And of course, we will be talking about the not the fairness. We will be talking about the performance mostly. Because the locks are the very used synchronization primitives, and in the multiprocessor, most of the overhead coming from the locks. Because if the locks were perfect, then you will get almost optimal parallelism possible. So the main goal of this talk is to talk about its time overhead. This is the kind of common example of using the lock. You just have some preparation section. For example, you want to put something in the set, then you have a very fast non-concurrent set. You take a lock, put this into the set, get some information out of the set, maybe the previous value, unlock it, and go in the section where you return something or calculate with it. So that's kind of the common pattern of how you're using lock, of course. And I've decided to separate the locks into the three parts. The first locks that I guess all of you are aware about are test and set locks, or simple locks that use just one register. So this is a simple lock. The ones that I guess some of you have worked previously, but I'm not sure whether you're aware of its insights. There are queue locks. For example, if you worked with Java at all, reentrant lock, for example, is based on the queue. The idea is it is kind of fair lock. Somebody comes to the queue and waits until the lock will be released. And there is the final that are most unaware type of locks are hierarchical locks. I will explain a little bit later why they're really necessary, but the core idea is that they were invented for NUMA architectures. We will also talk a bit later. And the idea is that you have their level of locks on the topmost, bottom, go, and so on and so forth on the lowest level, and you try to take the lock on the lowest level. When you're given this lock on the lowest level, you can try to attempt on the next level, and so on. So you kind of have to take k locks if you have k levels. Okay, the k locks, and if you took the lock on the highest level, you are happy, you finally got the final lock. This is the simple test and set lock. You just try to compare and swap it from false to true, and otherwise, and similarly, you unlock, you just set it to false. It becomes a little bit more complicated. This implementation becomes more complicated when you have a high load on this lock. So you have enormous amount of threads that are trying to take this lock. For example, already 10 plus threads. Why so? Because there is a large memory. If the critical section is small under the lock, you have a huge memory traffic on this locked cache line. The standard way on how to solve this problem on the memory bus to reduce this is to have a backoff. I guess you've heard something about exponential backoff. But the key idea is that if the lock is still locked, we just kind of sleep for a while or do some active stuff that nobody cares about. So it looks like that. We have a while locked. We just check that it is locked. We go to the backoff, and in backoff, several times we just try some active spinning. In the exponential backoff, for example, the number of times you spin grows exponentially. Depending on the time how much you tried already to take a lock. Otherwise, you just go to sleep. This works with OS threads very well because you can sleep at any moment. You can get context switch at any moment by their operation system scheduler, and generally, you can just simply sleep. There is no problems with that. We will see that this will be one of the biggest problems with lightweight threads. Okay, so this is test and set. Now we are coming to a more complicated queue. Queue lock, we will take the most common MCS, which is Miller-Krummy-Scott lock. And the idea is pretty simple. You just try to insert yourself to the tail. And then, kind of on the guy to the next, you see it is just waiting on its locked variable. And when the owner releases its lock, it just says, OK, I will set the next variable to true, and the lock is handled to the next thread. This is the code. Again, the code is simple. You just try to put yourself into the tail, and you wait on this locked variable until it is unlocked. The unlock, all other code is just for the corner cases, really. And here you just set the next guy to be unlocked, and that's it. Kind of, what is the problem here? If you're working in or with normal threads, this while also has a problem that it is just active spinning, and you have no idea when you will be getting there. And their normal usage of their MCS lock is that the guy just go to sleep here. So at first it just waits a little bit, makes some active spinning on there, and if there are not some for a long time, it just went to sleep. And it will not be scheduled by OS scheduler until it is unlocked by another guy. Okay, this is just for the NUMA lock. Oh, sorry, for Q lock. Now we're coming for the hierarchical lock. I told that they're created for the NUMA. So what is NUMA? All the machines that you have in your company, I guess, just kind of known as Intel Xeon or AMD Threadripper you have on your machines. Usually one machine contains several of these chips. But unfortunately, you cannot have the same memory access to all the memory there, because each chip there has kind of its own local memory that is really shared, but it has own memory. So the idea is that you do not have four chips connected to the same memory, and they have the same access time. No, the memory is split into the banks that is local to each of the chip. And in each chip, when you want to access another's memory, you have to pay much bigger than you're accessing your local one. So that is why there are coming hierarchical locks. They're mostly done for NUMA. Their idea is that I will try to pass the lock not to the next guy in the queue, but try to pass a lock to the next guy on my NUMA. Or in my like, there can be more NUMA hierarchy. There are several levels. And their MCS lock, hierarchical MCS lock, is known as like, you have on different levels, you have like this locking, and you will try to pass the lock on the lowest level several times, then on the second from the top layer, and going up. There is another one performance boost that will appear in the lightweight thread locks with this more precisely like the next lock, which is a cohort lock. Cohort lock is just like 2-level one, and the cohort lock you see is just like KQs, KMCS locks by the number of the NUMAs, and the global lock is test and set lock. So when you kind of became the first in the queue, you can try to take a test and set lock. And by the result, you also get a very nice performance boost, even not for the NUMA. Previously, for test and set lock, we have some backup strategy and etc. Here, for example, their main interesting result is that you have only K threads trying to take test and set lock. So you kind of reduce the contention of that lock, and you get the better performance. OK, great. Yeah. Also, there is a fast path and slow path. Fast path is just to take the global lock directly. Otherwise, go into the queue. OK. Now we've covered different locking policies and different locks. We're coming to lightweight threads. And OK, so you're here. I hope almost all of you are C++ developers. Maybe not, but interested in C++. You know that in C++ 20, they represented like coroutines. Unfortunately, for C++ 20 coroutines, they're stackless, so they cannot kind of replace the real OS threads as they are. And in the wild, there exist lots of different implementations of really lightweight threads or coroutines. So the C++ 20 are really kind of the coroutines, and we're talking a little bit more about lightweight threads. There are like confusion in the terminology usually. But the thing is that lightweight threads, or coroutines in our case, they're just fibers. They're just the replacement of real OS threads that has smaller context switch. But of course, you cannot get anything for free. And you have the problem that you have your own scheduler that schedules these lightweight threads. In addition to that, you have to program these lightweight threads much more like error-prone. Why so? Because you cannot context switch at any moment of this lightweight threads. You are not operating system. You cannot just take any thread at any moment. You have to introduce yield instructions, so for the context switch, so that your real scheduler that runs on top of the OS threads will understand how to schedule them over OS threads. Hopefully, it's not. I made it very complicated to understand, but the main idea is that on top of OS threads, you have scheduler of lightweight threads. And this scheduler of lightweight threads running the lightweight threads on top. So kind of you have more hierarchy here. But what is the problem with the lock? So suppose you take your normal lock and just try to use it with lightweight threads. So here is an example, simple example. You have one large OS thread, like one OS thread, and two lightweight threads. And they're first thread took a lock, do something, and switch the context inside your critical section. And the thread one, since your context switched, the scheduler decided to choose the thread one, and it says, OK, I want to take a lock, and I will spin there. But you didn't have yield. Simply, you didn't have yield in your lock implementation. So you're totally stuck. You will never get rescheduled again, because you cannot do context. The scheduler of lightweight threads cannot do a context switch at any moment as it wish. So we got a deadlock somehow. That's the problem. We have to solve it. Of course, like the simplest thing that you can that may come to your mind is just to put yield. But this may be not very performance efficient generally. We'll come to that later. Also, like about schedulers, regarding NUMA, we already have the NUMA. So the schedulers are also not very trivial, and they can be also as NUMA friendly and non-NUMA friendly. The standard thing is, the standard scheduler is that you have just a pool of threads, and there is a scheduler. It sees like which thread is free and just schedules like from the same pool. But for example, if you want like NUMA scheduler or something like that, you may have like different pools for each of process or a thread. You have each pool separately, and when an OS thread becomes empty, the scheduler tries to take from the same pool at first, and if it is empty, it tries to steal from somebody else. It's commonly known as work stealing scheduler, and it's can be NUMA aware, for example. This one is a little bit slow, generally, because like sometimes it is used just as a queue, like this pool. So mostly like fast libraries use the right part of work stealing scheduler. Okay, and what we have as the waiting right now. So previously we had the waiting active spinning and sleep. With the lightweight threads, we have two. So we have active spin, we have yield, still like context switch, and we have suspend resume. We will try to have suspend resume. The idea is that when you run suspend, you kind of make yield, but your thread will never be scheduled at all until it is resumed. It's a very nice trick. The same as with sleep, kind of for the locks, is that you will never schedule the thread that does some meaningless job until it is woke up. So it's reasonable try to use suspend resume. There will be problems because like not all libraries support the suspend resume function. Okay, so we are. Oh, I'm running too fast, so I will slow a little bit down. So right now we're coming to the nice part, like kind of to the main part of my talk, is that I'm trying to explain you how it's possible to update the mutex for the lightweight threads. It will not be rocket science, but in their evaluation you will see that there are definitely problems with everything that comes with any implementation of the mutex. So. The plan is pretty simple, so we will talk about like the common waiting lock with the backup strategy, understand what backup strategy can be used for test and lock and for MCS, and talk about NUMA-aware implementations. So we have like this waiting loop. You've seen it before already in my talk. We have a while condition, is that whether it's where the lock is locked, really. We just have while, and we make some backup strategy, and it's different for example, for test and set. We have two layers. We have active spinning plus sleep with some backoff. And for MCS, we really had also the same. We were kind of waiting. We were active waiting, and then we went to sleep. Okay, so we have right now, instead of two, so active spinning and sleep, we have active spinning, yield, and suspend and resume, or suspend. Unfortunately, for test and set, you cannot use both, right? That's unfortunately the problem here. You have only registers, one register, and you do not have any information about the lock. So you really, in test and set, you cannot make a suspend. So suppose for a moment you make a suspend. But how somebody will learn whom to resume at all? Because it doesn't have any information. For the MCS lock, we already saw that we have a specific node for each thread that is added. And we can just incorporate in that node an information on how to resume that thread. So for test and set, we can make only yield, and for Q locks, for example, for MCS, we can make both. The code is pretty trivial. So it's just like we do several times we do active spinning, several times we do yield, and several times and finally we do like the proper suspend otherwise. Okay, nothing pretty tricky. Right now, this is pretty important. Like this part is pretty important for spin and yield because we already saw that if you do not yield, you cannot make a deadlock. But before kind of yielding, yield is also not the free operation, right? So it has to be rescheduled. So maybe while taking the lock, you want to wait for a little bit to be active. So you will not yield at the start. So you will spin a little bit. Maybe the lock will be taken away really briefly. It will be unlocked really briefly. So we will wait a little bit. And that only otherwise we will try to yield. And suspend as our last resort if nothing really happened. So this is afterwards, this is the whole TTAS implementation. We just replace the backoff policy that we've seen at the start with their new backoff policy. The code remained the same. Okay, what's with their MCS log or Q log on how to pass the log to the next guy? And here comes the problem, unfortunately. So how it worked? So we were waiting for a log. Then we decided to suspend ourselves. And the suspension is not really that fast, so it takes some time. And if you decided to give the owner of the log tries to pass you the thread, and it tries to resume you in the middle of your suspension, you can have a problem. So with OS threads, it's usually that you kind of send a signal, please not to suspend, and it kind of doesn't matter in what order you do this. Unfortunately, this is not in our case. So if you do kind of resume before the suspend has finished, you are cooked. So you will never resume really the lock. It will not be resumed. Even that you call concurrently the suspend with the resume, you may not possibly to resume really the flight with thread, and you have a deadlock again. So how to avoid this problem? So really we need to force us to make the resume only when the suspend is finished. How to do that? The idea is pretty simple. So as you remember, anyway, we have to store some information how to revive the thread that is sleeping. So we will have an additional register that will store information how to resume the light with thread. And for that, we will store just two special values, 0 and 1. It's just kind of, it's ready to suspend, or it was really resumed already. And the idea is simple. So we just if we're trying to suspend, we just try to compare and swap from 0 to the suspend data. And the resume thread will see that you just did this, so I have to wait. It says that it's no longer 1. And that's it. That's it. You just have a compare and swap kind of in both parts when you try to make it sleep and you make to resume. And for this, for suspend, for example, you're trying to compare and swap. If you were unlucky to make a compare and swap, so that means that somebody has tried to resume you. We just spin and yield. Otherwise, we just suspend. So there is nothing really complicated about it. Okay, so we went over to simple and Q locks, and we come to the NUMA thing. And with the NUMA thing, right now, it becomes not very trivial. The main problem is we've seen that it mostly depends on the scheduler, where the lightweight threads will appear later. So when it is yield, it may appear on any other node. compute node. And when you're an owner and trying to pass to the next guy in the queue, this next guy in the queue, when it will resume, it really may not be on the same NUMA node already. So we kind of lost our NUMA locality that we wished for. That's pity. But we really cannot do much about that. There are several ways algorithmical ways that we predict that we can overcome this, but we didn't do this. The first thing that can solve this problem is to use NUMA over a scheduler that tries to take the next, tries to maintain the threads on the same NUMA, because as you remember, we have kind of local pools for each of the NUMA node. And the node, when it has a free OS thread, it takes from the local pool. So hopefully, we will be left on the same node, but it's not guaranteed. The other attempt that you can potentially do is that you can wake up already when you are the first in your queue and you're maintaining the lock. You already wake up the next guy, so that in the future you will know, you will have k active threads running, really, the first in each queue, and you will know potentially to whom to pass. Hopefully there will be a guy from the same NUMA. Okay, we didn't test that. That's my hypothesis that this algorithm may potentially work. Right now, we only use NUMA over scheduler from the libraries that we chose to implement with. But an additional note here is that we still have a very nice property of this hierarchical lock that we have a lower contention on test and set still. So it's not NUMA already, but it's kind of limiting the contention, which is already good for us, potentially. Okay. Now we're coming to implementation details on how and where we implemented it, all the code. So here is the QR code to our kind of library or just for the code. You can look how it was really implemented there. We just will try when we will make since we are trying to continue the research, we will pop more information there. So this will be the same repository for the whole time, I hope. So we took 3 target libraries for lightweight threads. These are the most common ones that appear in the world. So the first one is the Argobots. Argobots, it's a very, very nice library. It's pretty fast, as we will see on the experiments. It's really good. But there are some problems with that, is that it is academic project. And it has lots of tweaks and tricks on how to properly tune it. So if, for example, you want to get out of the box, you can take Boost Fibers. Boost Fibers is just, as you may expect, it is in the Boost library. And definitely it is quite good. It also provides NUMA over a scheduler. And if you do not want to make a lot of settings, I would suggest you to go with Boost Fibers, maybe. And finally, we took the library from our beloved Yandex, which is uServer. I think maybe you've heard about it. It's also a pretty nice library, kind of for lightweight threads for microservices mostly. So it has some downside also. We will see, all of them has different downsides, and we will see what is the problem. Right now, I will be talking, so we know that all of them support yield. So all kind of libraries with lightweight threads support yield. And the question is how to support suspend and resume. again, I like the word note, and here I want to note again, our choices of suspend and resume maybe not as optimal as they are in the libraries, because we weren't able to find, like, not all libraries support like suspend and resume out of the box. So we have to do specific tricks to make it work. Luckily, Argobots has suspend and resume because it's a very large library, like for academics. So it's definitely working good, and it has exactly this problem, is that you can resume only when the suspend is done. So that is why we had this complication with MCS lock additional to support Argobots, and I mean all others also, but we started with Argobots and we stuck with that for a while. For the boost fibers, we use the promise. For the promise, we create a promise, we get a future with wait, and to resume it, we just set the promise to true. It's not the best way to make suspend and resume, definitely in the boost fibers. We are unaware of any better. We are trying still to investigate that. The problem is that this approach has the locking at the back. And it will highly affect their algorithms that use suspend, really, like that heavily uses suspend, especially MCS lock. Finally, for userver, we found a way, so we will have single use event that from which we call wait non-cancelable. And to resume, we just said that the resume event.send. And it will emulate our suspend and resume. Finally, the most interesting part, experiments, and why we covered this enormous amount of locks before. We had a very simple, lightweight benchmarking that I will show here. Is that each lightweight threads will run for some times. It will call just simple operation. The simple operation just take a lock, run some critical section, unlock, make some parallel section or parallel work, and yield. Yield we're doing because if we do not do yield, and we will potentially get a starvation of lightweight threads. So it's a good idea to show yield, and it will show how good our locks with the collaboration. So for example, you can remove yield, you can run the lock, you can use the same lock as you have with OS threads, and it will kind of work in our examples partially. But what I'm saying is that if you're not doing yield, only the pack of threads will be working. And we will do not have really fairness, and we will do not have the real scenario that happens. So yield is important here. Okay, so we have 4 our locks re-implemented, like TITAS, MCS, HMCS. This is like the simple version of 2-level Q and Q lock. And NUMA MCS, as you remember, like this is the Q at the bottom and TITAS on the top. Also, we compare it against mutexes of the libraries that are provided. Now continue with experiments. So we have the critical section and the parallel section as the parameters. The first one is the parallel for, where the critical section, in the critical section, you will have a parallel loop with 12 tasks. And this is also to show this experiment to show the collaborativeness and how well we are working with suspend. Because if you do not do a suspend and you do just yield, you will have a bunch of threads in the running pool. And to take these 12 tasks out of the pool, you have to pay some time, because you have a large pool until you find these 12 tasks. And if you are doing suspend, this pool will be shorter and you will take these 12 tasks much faster. Great. The second is typically used for NUMA locks. The idea is that in the critical section, we just read 2 blocks of cache lines and update it. It takes the NUMA is that when you pass the NUMA lock to the next guy in the NUMA lock, it's that these blocks of cache lines are already loaded onto this NUMA, so it will save some time. So when you want to pass the log to the same NUMA node, potentially it will be faster. Okay, so we run on 96 hyperthreads machine. For some time, we had like 5 independent iterations and taken the median. At the OX-axis, you have the number of lightweight threads. 96 is somewhere in the middle. It's kind of a little bit tricky scaling here. It's double exponential. And the throughput on the Y-axis is the number of operations done by all lightweight threads in milliseconds. So here, test and set works the best. There is some potential explanation that the critical section is too large, so you do not have a lot of the problems with test and set lock. That is why it's pretty good. You don't have enough contention, but you see, like they work approximately the same. Like test and set, like a little bit better, marginally better, but all others are the same. The original lock of Argobots works worse. We dig a little bit into that, and Argobots uses really test and set, which is not fine-tuned generally. So it's just ours is a little bit fine-tuned for the machine itself, so that is why it works much better. For the boost fibers, test and set lock against works the best. And NUMA MCS lock as TTAS works approximately the same, and it is really important because NUMA MCS lock has this TTAS on top. That can usually be used as the fast path. So ideally, it takes like both advantages of Q locks and test and set lock. So we expect that NUMA MCS will work kind of the best. So, but in boost fibers, the TTAS works the best. I mean, this high rise, do not aware about that because their OX axis is exponential, so it's not that high rise. And as we expected, because of suspend problems with the locks, the MCS and the HMCS locks are working not very good here. Also, the fiber mutex, like the mutex from boost fibers, works approximately the same as NUMA MCS, so we expect that it works, it is implemented almost the same. Finally, for uServer, we took the experimental work stealing scheduler because with the standard with one queue, unfortunately, the performance of all the locks is the same because their main problems were lying in the queue, in the scheduling queue. And for work stealing, so you see the result is totally different. So MCS right now is the best, and TTAS is the worst. We do not find the proper explanations, but uServer mutex is definitely performing the best, and it's similar to their HMCS, really, as we found. Okay, this is for the parallel 4, so it's how cooperative our locks are. And with NUMA passing. With NUMA passing, for the Argobots, you see like HMCS and MCS became like performing the best. This time, compared to previously what we've seen. TTAS is already not that best. So here comes that NUMA or just Q is much better with this benchmark. For the boost fibers, the results is still like TTAS and NUMA MCS. You see like they perform almost the same, but NUMA MCS performs a little bit better than TTAS. Still, like just normal locks are dead. I mean, MCS and HMCS are dead. And finally, for uServer, they work approximately the same with the TTAS lying somewhere below. One important thing that I didn't mention here is I moved slides very fast, and you haven't seen the throughput. And it is pretty important, because for Argobots for parallel 4, you see the throughput was 30. For boost fibers, here it's 6. So it's 5 times margin. And their use server is also 6. So their Argo bots outperformed by a lot. That is what I told at the beginning. It's pretty fast. But with their NUMA part, that's pretty funny. The throughput for their Argo bots is like 200, maybe 200-ish. For the boost fibers, it's already 150, so it's only 2 times slower. It became 2 times slower. And finally, the use server is 4. So here comes the main takeaways. It's non-trivial to make like the normal logs for OS threads to work the same. So we have to adapt the logs. Secondly, it's very important when you want to use lightweight threads and logs there. Please think a lot about that. At first, which library generally of lightweight threads you're going to use, because it depends from like how easy it is to use and how performant it is. Plus, you've seen that already the results for logs are totally different depending on which logs are. I mean, NUMA MCS was reasonably well on all of them. So that would be the best choice, I think, but we will see. So when you will try to use the logs, please run experiments before, because for your workload, maybe some logs will be the best and maybe not. So please check it before. OK, so that is it. This is, again, the QR code for our project. I guess already, who wanted already find it. Their slides will be available later. And thank you for your attention. This will be the QR code for the feedback. Thank you.
Виталий, спасибо тебе большое за то, что так подробно рассказал про теорию и практику блокировок в легковесных потоках. И особенно впечатляет твои графики, где ты обыграл mutex Argobots в столько раз. Это, конечно, очень круто.
Thank you for the talk, Vitaly. Great that no mutexes were harmed during the tests. And now it's time to ask questions. Let's ask questions in both Russian and in English. We will send the mic.
Так, вот есть рука, пожалуйста.
Yeah, hi. The question was, you have chosen those three libraries. Like, did you do some sort of research? You have said that at some point of time you had to dive into some of them to see what's actually inside. And you said it's just basically TTAS. And why have you chosen those three?
OK, yeah. So the libraries were chosen because like Argobots is their kind of academia, top-notch research kind of environment, like kind of like is there. It has all the novel research in the lightweight threads. So like this is the most popular in the academia. Boost fibers is kind of one of the most popular in the world, really, with the in terms of the lightweight threads, really, with the stackful coroutines. And the use server was chosen as a very nice example where we can just test that our approach is kind of transferred to it. Use server is really used a lot in Russia, so that is maybe partially our choice for use server.
Thanks. Так, спасибо. Еще вопросики из зала? Так, если нет вопросиков, давайте вопрос от ведущего будет. Ну, это все для Stackful карутин, а все-таки есть Stackless. Не пробовали ли вы что-нибудь с ними сделать? Потому что мне кажется, что карутины в C++ 20, которые появились, они хоть и очень сильно абстрактные, но в принципе классная же штука.
That's a very good question. I would say we didn't try that. We I a little bit worked with their like primitives for the lightweight threads. For the coroutines, I worked a little bit with that, but we didn't yet dig into it, mostly because I think that their schedulers are not that fast, I mean, in the terms of stackless coroutines, I mean, right now. I mean, they're in the standard, but they kind of, you cannot tweak the scheduler or something like that just to experiment with that.
Yes, thank you. I think it's most dependent on which schedule we use, and we'll look in future to this. Окей. Кажется, что... А вот еще вопросик. Давайте последний тогда вопросик будет.
Okay, thank you for your talk. My question is pretty simple. What's the real-life application of having 1,000 fibers trying to lock on one thing?
That's a pretty good question, really. I mean, 1,000, maybe we took it too extreme just to show, but as you've seen on the results, it's on 1,000, like it's starting like from somewhere like from 200 to 1,000, it's almost the steep line. So I mean, like this is kind of the best, and we kind of by that we know already that we are good enough, like our lock is good enough, and maybe for the unreal number of threads. But there are 200 or something like that appear if you will try to rewrite MySQL, for example, MySQL to lightweight threads instead of OS threads. So it's already going there. And for example, like your machines like that we have, like this is not the largest machines that appear in the world. Like it's 96 hyperthreads, just 96 hyperthreads. I mean, you can take Threadripper, like the later, I mean, not Threadrippers, AMD Epic or something. It's already 100 plus, already cores at the start. So you can run like, usually for the lightweight threads, you would like to run like 3-5 times more lightweight threads. So you are getting already just a machine with like just a simple processor with 100 cores, you will already having 500 lightweight threads. So there is a reason. Yeah. So we are not talking about like the simple scenarios, right? Like MySQL is already kind of hard scenario, right? But there exist. This one is, for example, yeah.